Okay. I just finished grading the video. Okay, everybody's for number 3. Okay, a couple things I want to say it here. Several problems I noticed from this video. Okay, one is a couple of you exceed the 4 minutes time. Please, this is the 3rd time you do the video. You know, it's our length is between 2 to 4 minutes. I give 1 point for the length. Okay, so make sure you make your movie within the time frame. Okay, edit it and choose important information to show. And I think I only minus 0.5 for those of you exceeded the 4 minutes. Okay, but please keep it in the time frame. Okay, this is the first thing. The second thing is, I noticed 1 or 2 of you choosing the. I'm totally fine with picking the. I'm totally fine picking the homework problems, example problem as your experiment topic, but it's an experiment topic. You still need to do the experiment, okay? So it's not just explaining a homework problem, and that's not the purpose, okay? So it gives you some topics, what kind of experiment you want to do. That's good. I'm totally fine with it, picking some topic from the homework problems. However, you really need to conduct the experiment. I want to see the experimental design. How do you verify quantitatively the equation? Okay, so that please, yeah, just want to make sure. Okay. The third thing I still want to talk about is for some of you students show the verification part of the experiment. Okay, let me share my screen. Let me give you an example. It seems like everybody did a lot of you, not everybody, many of you did the Bernoulli equations. Okay, so let's see how we do the method. Remember, listen carefully. The Bernoulli equation, when you do experiment to verify the Bernoulli equation, it's not being verified yet before you draw any conclusion. So that equation is not valid, okay, until you prove it's valid, okay? Be careful, totally, just 100% remember what I said now, okay? So you use the Bernoulli equation to calculate something, or for example, velocity. Hey, many of you say, hey, I use the Bernoulli equation to calculate the velocity. No, that's not the end of the story, because Bernoulli equation hasn't been verified by you yet, okay? Your goal is to verify it. You calculate some value, use the Bernoulli equation, doesn't count. Okay, then you need to measure to verify that value you calculated from Bernoulli equation. Okay, does that make sense, everybody? Okay, so let me give you an example. Okay, so let's say Bernoulli equation. Let's help you with the experimental design. Okay, let's see what you don't have all the equipment. You know, I cannot measure everything. So I only can pick something to measure. So look at the equation, see what you're capable of measuring. Some value is easy to measure than the other value. So don't pick the difficult ones. Okay, let's say, hey, this is a Bernoulli equation. I always say, hey, you have to verify the equal sign. So everything you need to know to see if they are equal. Or in other words, you can say, hey, I use this equation to calculate the value, one value, but I measured that value to verify it. So that equation is right? When you calculate a value from this equation, basically you assume this equation is right, it's valid, but now our goal is to verify this equation. So before you verified it, it's not valid yet. Okay, so anything you calculate from it, you have to measure to verify. Okay, does that make sense to everybody? Okay, okay, let's see the waiting room here. Okay, everybody, still somebody in the waiting room. Okay. Okay, so please watch the video if you missed the early part of what my talk, the first 5 minutes. Okay, so you still have one project to go. So hopefully everybody do good on the last one. Okay, so again, this equation is not being validated yet. If you calculate any value from this equation, it's not valid yet. So you have to measure that value to verify. Okay, so so the assumption here to do experiment is this equation is not being valid yet. Okay, anything you calculated from it, you have to measure it to verify. Okay, to make sure that this equation is valid. Okay, although it's so-called Bernoulli equation, but it's not. A purpose of the experiment is to design the experiment to verify this equation. So it's not valid yet until you prove it's valid. Okay, so next question is, okay, what can I measure? I can measure in this equation. You see there are three components: P, pressure, elevation, and the velocity. If you are choosing to verify this equation, you try to design an experiment. Okay, think about at the beginning when you try to design an experiment to verify this equation. Look at the equation. Which thing is more easy to measure and which is more difficult to measure? That's why when you design an experiment, I want you to look at the equation you try to verify. It helps you to design. Okay, look at this equation: pressure, elevation, and the velocity. Which term is the most easy to measure? Which term is the most difficult to measure? I asked you to choose at least measure one quantity, right, in the equation. Okay. So you don't want to choose the pressure to measure because you need the pressure gauge. Okay, it's relatively difficult to measure. The easiest thing to measure is elevation. Okay, so you can actually measure elevation compared to the calculated elevation. That's one thing. That's one option. Okay, I don't want to tell you what experiment directly. It's your job to design an experiment, but I'm telling you the way. Okay. The second easiest thing to measure is probably velocity. Okay, so do you think so? Velocity is relatively easy because if the velocity is constant, if you have a cup, have a volume, then if you can measure the time fill this cup, is that the velocity? Volume per time. Hey, see, flow rate, then divided by cross-sectional area. It is the velocity. Okay, so it's measurable. Okay, elevation is easy to measure. Okay, pressure, like I said, is difficult to measure. If you have a pressure gauge, go ahead and use it. Sure, that's easy to measure if you have a pressure gauge. If not, okay, but just maybe avoid to measure pressure. So what do I need to do to avoid to measure pressure if I design experiment? So you design an experiment that pressure, maybe For example, if it's atmospheric pressure, pressure is zero. You can say, hey, it's zero. So I know the value, so I don't need to measure. So you design your experiment based on your availability of your equipment. Okay, if I don't have pressure gauge, let's design an experiment that the situation like the pressure is always zero, open to atmosphere, right? Or some other values you for certain. Okay, the water company tell me the pressure on in the force my water pipe is how many psi. I just assume that value. Okay, so something like that. So you can find out if you don't have a measurement, then in this equation, definitely you can measure something. At least you can measure elevation. You can design experiment just to measure, to verify the elevation. Or velocity is not too bad. You can measure velocity. Okay, so you can calculate the velocity, one of the velocity, and measure the same velocity to verify. Okay, does that make sense, everybody? I feel this is important. I watched a lot of your videos now, 3 of your videos, okay? I think half of you actually get it, okay? Some of the video I see, it's pretty good, pretty clear. It doesn't have to be complicated, okay? It's just a logic-wise, it's sound logic for designing experiment, okay? It's verification, I verified it. Even the error, how much error, I don't even care, okay? You have 20% error, so what? In fluid experiment, it's possible. Okay, some of you get like a 5% error, 4% error. Even in the video, you worry about, okay, that's some error. It's really acceptable. Okay, if you can explain the thing clear, everything, there's no holes in your explanation. Okay, the method you do the verification is sound. Then that's all I need. Okay. Hey, does that make sense? Is everybody listening? I don't see your camera, see your face. Give me some response. I really wanna grade everybody's video like everybody is 90, 9 out of 10, or 9.5 out of 10, something like that. Okay. Yeah, go ahead. Dylan, you have a question, right?
Yes, sir.
Yeah.
On my project, I was seeing your feedback, but I was just confused on like just the time because you said we had 4 minutes for
No, you
like
have 2 to 4 minutes. Look at the description. Your time
right,
project
right.
has to be between 2 to 4 minutes.
All right.
Yeah, that's what I said in the
Yeah,
beginning of today. Yeah,
all right. Okay.
yeah, yeah. Just please make sure. Yeah, good.
That's what I'm saying. It's like we only have 2 to 4 minutes to do it.
Uh-huh.
We having to introduce it, do the free body diagrams and all that in 4 minutes.
Yeah, exactly. That's also a skill for you to explain things efficiently in a time manner. Okay, that's all. Again, it's our purpose of the project. That's why I put 1 point for the time. So if I give you 1 hour, everybody can explain things well. Okay, but you want to explain your things. Your audience has no patience, most of the time when you talk to people. So you want to explain your things well within a time frame. Okay, that's also one of the goals of the project. Okay, so I can tell you explain. If you can explain that well, that means you fully understand the knowledge. Okay, that's also an indication.
Yes,
Does that
sir.
make sense, Dalen?
It makes sense. It makes
Okay,
sense.
okay. So try to organize your talk. Okay, it's really 4 minutes is really enough to show a principle experiment like this. Okay, so try to organize the way you say it efficiently, clearly. Okay, so it doesn't have to be long. Okay, it doesn't have to be long. Okay, is that good? I just really want everybody, you see the last one, everybody score like a 9 or above. Okay, you can, definitely can. Ask some of you, you see your score 9 or above, right? Some of you improve a lot. And one student, I think last time is like a 6 or 5 or something, but this time is 9 because he gets the points and show the experiment very well. Okay, so I guess everybody can do it. Okay, it's not that difficult, but just try to learn the way how to design experiment. It's very important in your life, in your career, design experiment and how to verify stuff and how to then explain stuff, okay, as an engineer using a professional manner. Okay, it's really, really important. Okay. Okay. This is video project. Let's see what else. Okay, we have our time again. My final exam time. Please don't remember it correct. Okay, Thursday, the last day of the exam week. Okay, May 6th, 8 o'clock in the morning. Fresh Hall 101. That big classroom at the entrance. Okay, it will be 2 hours. You will have 5 problems. Okay, for covering the entire semester. Okay, so it's closed book exam. I will provide you all the information, all the charts, diagrams, everything you need, I will provide. Okay, so please be here. Don't miss that. It's 40% of your grade. You cannot afford to not taking the final exam, please. Okay, I will give you a review. Okay, not really a review, maybe Q&A. Okay, on Tuesday that week. Okay, class time. So I think everybody should be available. Class time. So this is still 9:30 to 10:45. Okay. If you don't have question, I give you a review. But if you have questions, please prepare your question. Okay. Just don't ask me the question like, okay, what is a final exam problem? No, I don't answer that. But prepare your specific question. If you practice some homework problem, whatever you don't understand, cannot figure out, prepare it and ask during that period. Okay. I will give you a run through for the entire contents will be covered, but that will be quick. Maybe I spend take me like 20 minutes to cover, to give you a quick review. But I really want you to ask me questions. Okay, show you prepared and have some questions. Then I can help you. Then you can improve. Okay, so that's the help section. Questions? Okay, good. Today, let's continue on the momentum. Let's finish it quickly. And we have one content to give you, the piping system. So it's a combine of the chapter 7 and chapter 10. I don't cover everything in chapter 7 and chapter 10. I give you the way equation to solve for the entire piping system, which is very important to you in the future. Okay, so that's after today. I'm gonna finish the chapter 6 here. Then maybe I can introduce the chapter, the next, the pipe system equation. Okay, next time we'll give you some example how to solve piping system with a pump, with a with a turbine, those kind of things. I think it's very practical. Okay, but quickly let's finish the example last time in the middle of. All right, we didn't finish that elbow conservation momentum. Let's do a quick review. You really need to follow this procedure for solving conservation momentum problem. Otherwise, there's no hope. It becomes too complicated to you. Okay, engineering problem always become complicated eventually, practically. Okay, that's why you need to learn the skill, follow the existing procedures that previous engineer or scientists already developed for future engineer to use. Why not using it, right? So follow the procedures. Okay, then it will help you lead to the answer. Okay, not everybody can be an engineer. Engineer, you have to have some special ways to solve problem. Okay, so for solving a conservation of momentum problem, you really need to draw the free body diagram and the momentum diagram, the two diagrams. Okay, one show you all the components in the force, in terms of force. One shows all the components of the momentums, because conservation momentum is force equals to momentum. Okay, momentum is just force. Okay, same thing. So by looking at it, you see the force, right? But so that's why it's, you know, by a free body diagram, you can see all the forces. But in the movement part of a fluid, then it will have momentums. Okay, so the summation of force should be equals to summation of momentum in each dimensions. Okay, that's basically, that's what conservation momentum is. Okay, so last time we did diagrams, we did X direction. You see, look at this. Let's have a quick review. X direction, Y direction, Z direction is separated by it. We have an equal sign, right? Separate the force and the momentum. Okay. Okay. So look at the X direction. So X direction force based on the correct drawing. Okay, that's why draw free body diagram is so important. Then you can, if you have a correct drawing, then you can just follow the drawing. Okay, so you will see, hey, Fx, okay, positive Fx, positive Fp1, okay, a negative Fp2 on the X direction, okay, so it's cosine 30 degree times Fp2, okay, these are all the three forces on X direction. Okay, so two momentums on X direction. Momentum in, m1 v1, m dot 1 v1. Momentum out is the component of the m dot v2. Okay, X component of that momentum going out. So out minus in. Be careful, out minus in. Be careful, the minus sign is always there, but the out and the in, either could be, each one could be negative. Okay, although this problem is both of them positive. So positive out minus positive in, okay? But so in the Y direction, you see actually the out momentum is in the negative, is in the negative Y direction. That's why there's a negative sign in front of the out momentum in Y direction, okay? So both terms could be negative. Be careful. If you put the sign wrong, it's totally wrong, okay? Okay, stick with the principles, okay? Y direction forces, summation of forces. You have two forces in Y direction, the supporting force to hold the band, which is unknown force Fy. Then you have a positive Y component force from the Fp2. Okay, so sine 30 degree Fp2, Fy. Momentum, there's no inlet momentum, no in momentum, so in Y direction, it's zero. Out momentum, see, it's going downward. Downward is negative Y direction. That's why it's negative m dot v2 times sine 30 degree, which is the vertical component. Okay, so this is x, y, z. Anybody? Give me the z direction equation. So fx is our summation of z also equals, right? Fz, you have Fz force to hold it. Okay. Then the weight, right? Weight seems going downward, right? Okay. Z is the third dimension. Okay. So going out of the paper is positive Z. Okay. Gravity is in the negative Z. So it will be minus the total W. It's empty weight, and also the weight of the liquid, gamma times volume. Okay, I directly write down gamma times volume. Do you know what that means? Okay, in this class, I want you to use gamma as a property, right? Specific weight. So calculating the weight is gamma times volume for the fluid. Okay, can you memorize this? Okay, you have to remember some equations. There's no equation sheet. Okay, I will provide all the charts, diagrams, tables, properties, but I will not provide the equations for you. You have to memorize all the equations needed for this class. Okay, gamma times volume. Okay, it's not that difficult to memorize, just remember. Okay, gamma fluid times volume of the fluid, it's the weight of the fluid. It's rho GV basically, right? Rho V is mass, right? Mass times G, mg is weight. Okay, memorize it. How about the momentum in Z direction? Anybody can give me a value?
0.
0. Yes, that's so easy. There's no motion in the Z direction, no momentum out it's just a wall, right? So go, bingo. Okay. So look at this equation. Do you have everything? See, each cycle has 3 equations: fx, fy, fz, 3 equations. So fx is our unknown, fy is our unknown, fz is our unknown. So do we have everything else? If we have everything else, we can solve the fx, fy, fz. Anything we don't have? Now it's time for you to look at it. Look at all the information you have. Okay, see, before this point, I don't even look at the information I have or not. I just write down, use letters. Okay, now it's the time. Anything we don't have?
We don't have something to find the area of the pipe.
I think that should be given. Is that right? Let's look at the problems. I might not write it on the paper. I think it's 1 meter diameter. Okay, just let's confirm. Yeah, I said 1 meter. The first sentence of the problem statement. It said diameter, 1 meter diameter. Good. When unknown, we find it out. Not unknown, one value, we find it out we should have. Okay, diameter 1 meter. Anything else we don't have? Look at the equation. Go do it. Go do it with me. In the final exam, you're gonna do the same thing. So let's just practice it here. Do we know FP1?
We can find it.
Yeah, we can find it. Pressure times area. Okay. Can we find FP2? Actually, it's the same thing. FP1, FP2, right? They have the same pressure today. Yeah, 75 kilopascal, right? 75 kilopascal. Okay, the only difference is the cosine 30 degree or some sine 30 degree. So FP1, FP2 are the same. Cosine 30 degrees there. Do I have the mass flow rate? Okay, good. We can calculate it, right? Not directly, we know the Q. So based on the Q, we should be able to find the mass flow rate. Okay, good. Can I find out the V2 and the V1?
Find that from Q also, right?
Yeah, find out from Q. Q divided by area. That's it. All right, V2, V1, everything we know. Okay, good. For the first equation, everything else we know. So we should be able to find out Fx. Second equation, same thing. FP2, we know. Basically the same thing. We know everything. Okay, so third equation. W, empty weight, it's give you 4 kilonewton. Be careful, use 4,000 in the calculation. Do I know gamma? Gamma of the fluid?
Did we say it was water?
No, it didn't.
It's we have the S, so we can find it.
Yeah, we have the S, right? That's a specific gravity. So it's 94% of the gamma of water. Okay, so the gamma of this fluid. Everybody? See, that's a testing point here. To test you if you know the gamma, calculated gamma from the specific gravity.
Dr. Zhang, could you
Yeah,
read your Z equation again?
Fz minus the empty weight, W empty, right? Is that right? Can you write it down yourself? I think I worry if you can't write it down yourself, that's the trouble. Empty weight, right? Then minus the gamma times the volume of the fluid, right? The total weight, okay? Empty weight plus the fluid weight, okay? So we get gamma. Do I have the volume? Yeah, it's given. Okay, you should be so confident at this point. Okay, I'm good. I think I can calculate fx, fy, fc if I'm careful. Now it's just calculation. Okay, so these are the forces required to hold this band in place. Okay, because of the momentum, you need to have the force to hold it. Otherwise, this band is going to be shoot away. Okay, by the momentum from the fluid inside the band. Okay. Everybody, any questions? This is a relatively complicated problem, 3D, right? Okay, so that's the standard procedure. Okay. More complicated problem could be in the outlet, the velocity is not uniform. Okay. If the velocity is not uniform, no, you can't use, okay, let me use another page. Okay. The example, I don't have time, but I show you, I tell you the example you need to look at, okay? If it's non-uniform velocity, then the example 6.6, you read it yourself, okay? But let me tell you, what should you do differently? Everything else is the same, the equation is the same, right? Summation of force, okay, equals to momentum out minus momentum in. But if one of them is, let's say momentum in is, it's constant velocity, so it's just this momentum in. But if the momentum out is not, then problem is here, mass flow rate, you know, you need to use integration to calculate the mass flow rate, right? Okay, then your integration mass flow rate is what? Do you remember? Density times VdA. Okay, so but you have actually another V, velocity here. Mass flow rate times velocity, that's the momentum. So in the integral form, actually you have to time another velocity here inside the integration. It's not W, V times V. To make it a momentum. Okay. So momentum, if it's non-uniform velocity, it just become V squared dA. Okay. This is the momentum terms. In this problem, let's say momentum out. Okay. Here you will be rho V squared dA. Okay, that's the standard form if it's non-uniform velocity. Okay, both momentum can be non-uniform velocity. Okay, so I think the most difficult problem I can give is three-dimensional non-uniform velocity at the inlet and outlet. Okay, for force balance, not much different. Three-body diagram, same thing. But if it's a non-uniform velocity on inlet or on the outlet, then you need to use this form to represent the momentum in or momentum out. So you have to take some integration. Remember, we do the flow rate calculation. You really need to practice that. Okay, in chapter 5. Okay, you need to define the dA in terms of the the velocity. If velocity function of r, you need to take make dA into dr. Right? Remember, we do the circle. Okay, and in the example problem, we have another flow rate calculation or non-uniform velocity. So need to practice that integration. Okay. So that's the most difficult problem I can give you. I won't give you unsteady conservation momentum. We never talk about unsteady conservation momentum. Here, the equation here we talk about is steady state conservation of momentum, right? Okay, so yeah, steady state conservation of momentum. We don't deal with unsteady conservation of momentum. Okay, so steady state conservation momentum, but the momentum could be non-uniform velocity. Okay, just refer to how we do flow rate calculation for non-uniform velocity. It's the same way. Only difference is v squared instead of just v in the integration. But calculation procedure will be the same. Okay. Okay. Is that clear to everybody? Okay, I'm just trying to tell you how to prepare the exam. Okay, if the problem is conservation of momentum, these are the levels from easy to more difficult. That's possible in the test. Okay, so if you prepare, just prepare like that. Okay, look at the example 6.6. Maybe it's helpful. Okay, and also there's a similar, I think I have a homework problem assigned as similar also in the wind tunnel, and do some calculation for the drag of a flow over a object, an airfoil. Okay, to calculate the drag, use conservation moment. Also look at that, try to practice that example in the homework problem. Okay. So that's just the non-uniform velocity, but that's exactly the same way. I don't want to repeat it. Exact same way as we calculate the mass flow rate, volumetric flow rate for non-uniform velocity. Okay, refer to the previous notes and the video. Is that good? Anything? Any question before I move on to the piping system? Okay. Chapter 7 and 10. Piping. Okay. Let me draw a very practical situation when we use it in industry. Okay. Okay, do you understand the system? I think it's very common, right? This is the pump. Okay, what do you need a pump for? Pump serves two purposes. Okay, but basically pump is to give energy into the piping system. Is that right? Okay, it gives supply energy to the piping system, and the pump is for two purposes. One is to deliver the fluid from a lower location to a higher location. Is that right? That's one purpose. See, I actually draw this. A lower tank, the flow, let's say from left to the right. Okay. Okay, I put a pump here, is trying to deliver the water or liquid from lower tank to the higher tank. Without the pump, it won't happen. If gravity driven always from the high tank to low tank, it's not, never will have the opposite direction. Okay, if you want to deliver liquid from lower location to higher location, have to use a pump. That's one of the purposes, one of the two purposes. Okay, the other purpose is to provide the flow rate. Okay, pump is to provide the flow rate in the pipe. Okay, you wanted the flow in the pipe, but yeah, the flow is for it drive from lower location to higher location. But in chemical industry, petrochemical industry, sometimes the flow rate is necessary. They need to create a flow rate for some purposes. Okay, okay, for the reaction, for whatever, you need the flow rate. Okay, you need a certain speed of the fluid to make something happen. Okay, so that's the second purpose for the pump. Okay, so pump always connected to a piping system. Okay, you usually put a pipe right around the pump for pumps to deliver the fluid. Okay, so for this is the whole system. The whole system, there will be a system equation, which in chapter 7 will tell you a system equation for the whole system. Okay, It's very similar to Bernoulli equation. Actually, if you ask a plant manager here, what equation is that system equation? They tell you it's a Bernoulli equation. Okay, but what the textbook says is actually it's not Bernoulli equation. It's called energy equation in a piping system. Okay, it derived from the different origin comparing to the Bernoulli. Bernoulli is from the streamline, from the Euler equation. You remember we derived it. It's nothing to do with actually the piping system. It happened eventually look similar. And the system equation is derived from the conservation of energy, which is in chapter 7. Okay, so I skipped most of the conservation energy part, but let's just focus on the system equation for the piping system. Okay, energy equation for the piping system. Okay, it's okay. Just let you know, if you talk to your boss, your supervisor, they call it Bernoulli, you know what it is. Okay, you don't have to correct your boss, right? Usually. Okay, but you know they are actually different. Okay, this is actually the energy equation, but the equation look very similar. It compare from the beginning of the system to the end of the system from energy point of view. Okay, from 1 to 2. The equation is very similar to Bernoulli. P1 over gamma plus Z1 plus V1 square over 2G plus the HP. Okay, we introduced something called HP. It's called pump head. Okay, the pressure energy supplied by the pump. Okay, equals P2 over gamma plus Z2 plus V2 square over 2G plus HT. Okay, another thing called turbine. Okay, turbine is take energy from your piping system. Okay, if you have a turbine inside of your system, you have to include that and include that in the right-hand side of the equation. Okay, it's a turbine head. That's how much pressure energy can be taken from the system. Okay, you put a turbine, maybe you can make electricity. Okay, if you think about it, if the flow is opposite from 2 to 1, you can put a turbine there because the gravity, drive the flow. The flow will drive the turbine. You can produce some electricity, maybe. Okay, depending on the order direction of the flow and what equipment you put in there, and also HL. Okay, so this is really not a Bernoulli equation anymore. You have additional terms. Okay, you have a pump head, turbine head. I already talked about it, and also there's HL. What is HL? HL is head loss, loss head. Now, that's the first time we introduce the loss here, right? In Bernoulli, chapter 4, we never talk about the loss, okay? We assume it's a perfect system, ideal, okay? Then it's P1 gamma Z1, V1 square over 2G equals P2 gamma over gamma Z2, V2 square over 2G. That's called Bernoulli. They're equal. It's a perfect system. But in the real world, it's not perfect, never perfect. Okay, so that's why you have losses. Any system, piping system, you have loss. And it's very important. Sometimes the loss is huge. You cannot just simply neglect. So it will be in the right-hand side of the equation they call head loss. Okay, this is the complete equation. Okay. So my question is this: why is HP is the left-hand side and the HT and HL are in the right-hand side of the equation? And the 3 term in 1, it tells you the initial, how much energy you have initially in the system. Okay, now we really come back to the energy point of view. Remember when we talk about Bernoulli, I always say from energy point of view, right? So it's actually the same. You can actually think of the energy point of view here, really from looking at this equation. From the energy point of view, P1 over gamma is the pressure energy at the beginning, pressure head. Okay, Z1 is the elevation head at the beginning.
Excuse me, Professor, but we're having fire alarms go off in Colette right now.
Oh, okay. I don't know what to do. Where are you? You are at the C center? Okay. Yeah. I'm recording the lecture. Go ahead. If you have to leave, you have to leave. Okay. But we have a quiz shortly. Okay. Where are we? Oh, okay. Initial energy, right? That's initial energy the system has. Okay. HP is the pump head, so it's the energy supply into the system. Now you know why HP is in the left-hand side of the equation. The left-hand side of the equation total, they tell you how much energy totally it has in the system, total. Initial energy plus the supplied energy. Okay, that makes sense, energy point of view. So now you tell, okay, why are these two terms in the right-hand side? So right-hand side, it tell you what the fate of those energies, what eventually the energy goes, what at the end, what energy turn to. Okay, I like to use the fate. What the energy initial is, so much energy in the system, initial plus the supplied energy. Eventually, all those energy goes to, at the end, what's the energy left? What's the pressure, elevation, and the velocity? What at the end? Okay, some of the energy be taken to make electricity. Some of the energy disappears because of the loss, friction. Okay, so total, so much energy eventually just go to 3 places. Okay, well, of course, the first place is at the end. You have three components in that one. It become eventually what the end pressure is. What is the ending elevation? Okay, what is the ending velocity? Okay, and what is the so then the other part is some of the energy will be taken by the system if you put a turbine there. Let me draw a system there with turbine. Let's see, you have a reservoir on the mountain. You have a pipe drive the water down to the hill, down to the bottom. Then you can put a turbine here. Eventually there's a lower reservoir. The water eventually ended in the lower reservoir. Okay, so your elevation here, Z1 is higher than Z2. Totally potential energy, turn to the velocity, kinetic energy, then drive the turbine, eventually become calm in the lower elevation. So the difference in the potential energy turns to electricity. Okay, that's another example. Then in this case, if you want to write the equation between 1 and 2, that same equation, which term we don't have?
HP.
HP we don't have. We don't have a pump there. We don't need a pump. We have initial enough energy there. Okay, eventually it turns into at the end the P2, Z2, V2, then some loss HL in the pipe, and the sum of the energy goes to the turbine, goes to the electricity. Okay, so that's the energy principle. Today I don't have time to give you an example, but next time I will. HP and HT usually is spec from your pump and from your turbine. Basically, not much to calculate, okay? But not much to model. But HL, we can model it. Okay, let me give you the equation before we go to the HL. There are 2 parts of loss. Educated guess, what are the losses coming from? Let's say HF. What F stands for? Friction. Yes, you're right. Friction is one of the major reasons, right? And then we have, let's say, called fittings, everything, minor losses. Major loss plus minor losses. Okay, so minor loss, you have multiple, many different components will be contributed, because on the piping system, you have valve, elbows, inlet, outlet, maybe have a contraction, maybe have a flow meter, maybe have pressure gauge. Everything added on the piping system will contribute a little bit to the loss. So you need to model it, right? Each component will have a little bit each. Okay, so frictional head loss is easy. It's LF L over D V squared over 2G. There's an equation to model the frictional head loss. Okay, L is the length, D is the diameter. Okay, so it's proportion to the length. Longer it goes, more frictional loss it is, right? And also D is in the denominator. So the larger the pipe is, less loss it will be, right? So velocity is also in the numerator. Okay, higher the velocity is, more losses it will be. 2G down here. F is something called friction coefficient. Okay, it's a coefficient, just like in the solid mechanics, you have a friction coefficient, right? Okay, here you also have a friction coefficient. You can determine it to use Moody diagram. I'll show you next time. Moody diagram, very famous one. Okay, so that's kind of like need a little calculation in the front of the diagram. You can have it. And minor losses, you have so many components. Okay, so I put the summation of k v squared over 2g. V is still velocity. So the losses, minor losses, still related to the velocities. Okay, the greater the velocity is, the more losses. But the coefficient, minor loss coefficient k is from tables. Any different components will have a k value for you. We have tables in the textbook. Okay, for valves, for elbow, for bend, for all those meters. Okay, everything will have a different k. So it's not much. Basically, just looking to the engineering tables, engineering property. Okay, so this is the way how we model the loss. Okay, this topic is really important, very practical. Okay, you guys, many of you do the senior design project next year. You need to do the piping calculation. I'm pretty sure a lot of projects from industry, you really need, everybody need to know how to do the piping calculation. Very important. In your work, if you find a job here, you know, in mechanical, chemical engineer, you definitely need a piping calculation and the pump calculation. Okay, these kind of things. Okay. Is that good, everybody? Okay. It's not difficult, right, to understand this, right? It's really not difficult, right? It's just an equation to use to calculate the loss, okay? If you have the loss, then this equation is complete, okay? You can use this equation to calculate something, okay? This is a system equation in the pipe, energy system equation. Okay, let's start the quiz. Chapter, let me show you the quiz problem here. Please turn on your video now. Is that now it's the time to turn on your video camera? And do not worry about it. It's not really not difficult. It's very similar to the last quiz you did. Okay. Since last quiz you didn't do too well, let's do a similar problem here. Okay. Okay. Let's do a similar problem. Let me give you information for this. This is the problem. Okay. So you have here a liquid in there, water flow in this contraction. Okay. With whatever velocity. Okay. V in there. Okay. Let me see. Let me read it exactly. Got the information here. And the velocity value is, let's see, the velocity at the inlet station is, okay, I give you the velocity value, okay, V1, 10 meters per second. Okay, diameter, V2, D2 over D1. Okay, some of you in the waiting room. Okay, let me see if everybody turn on the video camera. I still didn't see two of you. Please turn on your video camera. Okay. So velocity is this. Okay. So your diameter ratio is 0.5. Diameter ratio, D2 over D1. Okay. I want in your paper, draw this location 3 and 4. Just like we did the last time, 3 and 4, okay? Okay, it's a mercury manometer, S equals to 13.6, okay? You know the goal right here is to calculate delta H. Okay, since this is the 10 feet, the English system, let's change it. Let's say this is a 3 meter. Okay, I don't know if it will be useful or not. Okay. Okay, so the goal is to calculate. Okay, what is the deflection in the mercury manometer? Okay, so it's super easy problem. You can do it, but I want you to follow my procedure here. I want you to fill in the blanks here. Okay, it's just several blanks to fill in. Okay, you have to follow it. If you use your own way, I don't give any points. Okay, everybody listening? Okay, so first step, I want you to write down the Bernoulli equation between 1 and 2. Point 1 and 2. Okay, write this Bernoulli equation. I will grade it. Just one line. I don't want you to write too many lines. Okay, write down the Bernoulli equations. You want to specify your location Z. You want to put your origin Z at 1. Okay, go ahead now. Write down the Bernoulli equation between 1 and 2. Okay. You don't need to get rid of any terms. I just don't want you to get rid of any terms here. Okay. Leave it there. Okay. The second step, hydrostatic principle, just like exactly same as last time. Okay. If you really still cannot get this time, that's your fault. Okay? I posted the solution already. Hydrostatic principle between 1 and 3, 2 and 4. Okay. Second line, I want you to rewrite this equation. Okay. For 1, turn the hydrostatic terms of 1 into hydrostatic term of 3. Okay. Hydrostatic terms in 2 turn to 4. Okay. So transform this equation become 3 and 4 plus the velocity, of course. Velocity you can still keep 1 and 2. Okay. I don't want to see in this line, the second line, I don't want to see P1, Z1, P2, Z2 in there. I want to see everything 3 and 4. Okay. Plus the velocity terms, V1 and V2. Okay, can you do that? Is my instruction clear enough, everybody? Okay, if you still don't know that, that means you didn't pay attention, didn't read the solution, didn't, study it. Okay, so that's my goal here.
So you changed that distance between stage 1 and 2 to 3 meters?
What's your question again? Change what?
The distance between stage 1 and stage 2, you're changing it to 3 meters?
No. Oh yeah, the distance here, I don't think you need this distance. Okay, don't worry about it. I don't think you need this distance. Okay.
Okay.
Okay, follow me, please. Okay, I just want you to focus on what I say. See if you can follow me. I just need a 2 line now. Okay, I will give 2 points on this. Again, 4 points on this line. Okay, 2 points. That's a correct way to solve manometer problems. Okay, so again, in this first equation, there should be 1 and 2. Okay, between 1 and 2. The second equation, it will be 3 and 4 in there, plus the 2 velocity terms, 1 and 2. Okay, I want you to convert the hydrostatic piezometric head, basically, between 1 and 3. Convert 2 to 4. Okay, don't put any number there. Okay, I only will grade this 2 line. Don't give me the third line. Okay, I won't grade. Okay, I just want the initial Bernoulli equation, then the converted equation. Use 3 and 4. End with V1 and V2. Okay, is that clear enough? Okay, next step. 2 points for the next step. This is 4 points. Okay, 2 points. the next step, also 2 points. Okay, find the pressure difference between 3 and 4. Using the mercury. Mercury part, okay? What is the pressure difference? And then substitute it into this equation. I think I probably give too many points on the second step. Second step is 2 points. You need to calculate the velocity later. I give you some points. Okay. So 2 point, 2 point, 2 point. So far, three lines. Okay. Find the pressure difference between P3 and P4 in terms of the mercury manometer in the delta H. Then substitute this into the second equation. So you become a third equation. Okay, your P3 and P4 are gone. Listen carefully. In the third equation for 2 points, your P3 and the P4 are gone, replaced by the manometer reading. Okay, the third equation I want to see 2 points. I should have give the paper, longer paper, only 1 page. Okay, only 3 lines. Okay, just make it to, you can use your scratch paper or whatever, okay, for the process, but I just need you write the 3 line clearly on the equation, on the solution sheet you're going to submit, okay? Is there any question? Anything not clear? I want everybody to get a 10 out of 10 this problem. Okay, that's my goal. Okay, any questions from you? Do it individually. Okay, don't talk to each other. You can do it. Okay. Anything not clear? Is that good? Okay. So the next step. Now the equation, in this third equation, you will see the delta H there, right? Your unknown is there. Is that right? And you have a Z3, Z4. You know the difference, Z3, Z4. Okay. Then you have V1 and V2. Okay. So the next step here, 2 points. Calculate the V2. 2 points. Calculate the value of V2. Because in the third equation, now you have everything but V2. V1, you have it, okay? Everything else, you should have it. Your delta H is there, okay? So you need to calculate the V2. Okay. Be careful. This is the information I give you here. Diameter ratio is 0.5. Okay, did you calculate V2? Now you have all the information to calculate delta H. The last step is delta H 2 point. Okay, I don't care what value delta H is. I make up this problem. I make up all those numbers. If delta H could be weird, okay, just check your calculation. Make sure it's right. I don't care actually how weird the value delta H is, too big or too small, okay, but any value, okay, but it has to be correct from your calculation. So this is the 5 steps I need from your solution sheet for this problem, okay. After you calculate V2, the 4th step, substitute V2 into the 3rd equation, okay, you should have everything in there. And you can calculate delta H. And the fluid is water, okay? So the gamma you're supposed to know, 9800, this is the SI system. Okay, so the summation side is open, you still have 14 minutes. It will be closed on 10:45. If you, yeah, if you know, if you have the approval from the disability office to submit later, you can submit late. Okay, it's fine. Okay. Oh, plus the final exam, if you need extra time from the disability office, they can schedule your test in chosen hall, okay, with 1.5 times time. Okay, please schedule. Otherwise, you need to come to Fresh 101. Again, you don't need that 3 meter. I put it in there. You really don't need that value, okay, if you go through this process.